Okay, so going to work generally in AD and V equals L of R, and just a couple of reminders. If you have a complexity class gamma, then and a model M, then we say M is gamma correct if it satisfies, it agrees its truth about that. Its reals satisfy phi x if and only if the true reals of V satisfy phi x for all the formulas in the gamma in this class gamma and the reals in M. So gamma might be some projective point class or maybe something beyond that. Then delta 1 n omega 1 is just the set of reals which are delta 1 n in a countable ordinal. So that's when a real x is in here if and only if there is an ordinal used to define that real, and we use sigma 1 n formulas phi and psi. And whenever we have a well order of order type xi, then for every integer, the integer gets into the real if and only if c holds of w and n, and that's if and only if not c holds of w and n. So it's delta, two sigma 1 n formulas there, right? Equivalently, because we're talking about sigma 1 n here, and maybe n is at least 1 in my. There's a xi, one sigma 1 n formula phi, and for all reals we have that y equals x if and only if phi w y. When w is again like this, as order type xi. Okay, so yes. Okay, and then some standard, well-known facts about some of these things. So the reals of L omega 1 ck, least admissible ordinal, are just the delta 1 1 reals, so with no ordinal parameters, so it's delta 1 1 definable. And this model is sigma 0 correct, but it's not sigma 1 1 correct in V. Up one level to L, the reals are delta 1 2 in a countable ordinal now, and L is sigma 1 2 correct. So it went up 2 quantifiers from here to here. It's not sigma 1 3 correct. And then the levels beyond there are the MNs. The reals of M1 are the delta 1 3 in a countable ordinal. This has exactly the same correctness as L has. And then in M2, it jumps up 2 levels of correctness, the sigma 1 4, not sigma 1 5, but the delta 1 4 in a countable ordinal, and then so on. M3 has, again, that same correctness, but it's delta 1 5 in a countable ordinal, and this pattern continues throughout throughout the MNs. We also have the following result that sigma 1 1 and pi 1 1 flips between V and L omega 1 ck. So by the Spector-Gandy theorem, the pi 1 1 truth in V about integers or about reals in L omega 1 ck is just sigma 1 1 expressible over L omega 1 ck. And conversely, pi 1 1 truth in L omega 1 ck is sigma 1 1 expressible in V. So these two flipped like this. So although it's not sigma 1 1 correct, it still defines the sigma 1 1 truth in this opposing way. And that's moreover, that's recursively, uniformly recursive. So there's recursive functions that map pi 1 1 formulas phi to sigma 1 1 formulas psi phi and rho phi here. And so the V satisfies the pi 1 1 formula if and only if L omega 1 ck satisfies this sigma 1 1 formula here. That's recursively produced from phi here. And likewise in the other direction, there's recursive mapping like that. And so this goes up through the MNs as well, on the odd sides of the MNs. So in L, as I said, L is not sigma 1 3 correct. And in fact, there's sigma 1 3 truth in V restricted to its integers, which is not L definable. For example, 0 sharp is a delta 1 3, which is not definable over L. But sigma 1 3 gets, although M1 is not sigma 1 3 correct, it can compute sigma 1 3 truth, and it's likewise in a recursive fashion, it flips in this sort of way, just like for L omega 1 ck. So pi 1 3 over V is sigma 1 3 expressed over M1, and conversely, pi 1 3 over M1 is sigma 1 3 over V. And I'll remind you in a moment how this works. Okay. And then likewise, as we go up through the higher MNs, on the odd side, we always have this inversion of truth here. Okay, so we're going to look at generalizations of this in levels of L of R. So this is always in the L of R. The definability is always in the L of R language here, which is just language of set theory with a constant symbol for the reals. So we can always refer to the reals. And and then a slightly reduced hierarchy, sigma 1, well, so is defined as follows. Sigma 1 reals is just sigma 1, and we're thinking about defining over J alpha R here. Pi n R is just the negation of sigma n R, and the difference is that sigma n plus 1 R involves just a real quantifier, existential real quantifier over pi n R. So you just you go up through the hierarchy doing real quantifiers instead of quantifiers that are allowed to range over the full J alpha R. They only range over the reals, but the sigma 1 at the start is over the full J alpha. Okay, so that gives us sort of two, I mean, obviously sigma 1 R is sigma n R is contained in the usual sigma n, but it's not clear the other direction. Okay, and then OD alpha n, this is generalizing the delta 1n in accountable ordinal. So OD alpha n is the set of reals such that for some ordinal xi, accountable ordinal xi, and some sigma n formula phi, for all reals y equals x if and only if J alpha R satisfies phi w and x. So x is a singleton, which is sort of sigma n in accountable ordinal singleton. Yeah, and then we can also, so that's OD alpha n. You can do the same thing with sigma n replaced by sigma n R, and that gives OD R alpha n. Ask what are the reals that we get in there. I guess we pointed out that in the version for delta 1n, I had the two versions of delta 1n definability. The first one where you look at you define the real as a set of integers. The other one where you define the singleton. And it didn't matter; these are equivalent. This can be different. For example, over sigma 1 over J alpha. So if you look at the other version, sigma 1 over J alpha, it might not be the same as this. Here I'm doing the singleton version, right? This is always just the singleton. The other version is also interesting, but here we're talking about the singleton, as opposed to defining the real as a set of integers. Okay, so yeah, I'm going to mostly concentrate on the case alpha equals 1, so J alpha R is J of reals. So this the notation I'm using, J0 R is just R, and J1 R is one step in the J hierarchy above there. And so in this case, the sigma n R and sigma n R is the same as sigma n. So I define these two hierarchies, sigma n and sigma n R. Actually, they're recursively equivalent in this special case. In general, that's not the case over J alphas, but for now it is. So I'm just going to, now we can ignore that superscript R, and everything's going to be sigma n and pi n for the present. Okay, so then we had the OD, the projective level, and the first one sort of beyond there is this OD 1, 1. So this is delta 1 in accountable ordinal over J of R. The first one is the alpha, and the second one is the degree of definability. So this is talking about over J of R. This is just sort of putting all the projective things together. So OD11 is the same thing as the reals that are in this m less than omega, where that's just the union of the mn sharps. You take all the reals in the mn sharps, they put them together. You can consider as a mouse by putting them in, extending them, because they extend one another. And that's a mouse, and it satisfies V equals everything is countable. Its reals are just definable. It's projectively correct, but not correct about sigma 2 over JR statements. Okay, wouldn't prove a general fact about lots of levels of the L of R hierarchy. The OD lambda 1 is the reals of a mouse for every lemma ordinal lambda, and his result was more general than this. Rudamina considered OD alpha n for certain other alpha n's, and showed that OD R alpha n is a mouse set. So, sorry, I didn't say what the m is. This is just another mouse here. For certain other pairs alpha n, with the main sort of focus being on uncountable cofinality alphas, where this is, sorry, I define, well, I don't really, I'll remind you what this alpha projective like is in a moment, but the basic point was Rudamina considered sort of this set OD alpha n for certain ordinals uncountable cofinality here, and some of countable cofinality in cases of that, but main focus on uncountable. Not right now. Okay, so now we want to look at ladder mice. So this is relevant, as Derek was talking about yesterday. This is relevant at just beyond the projective, well, just beyond. I mean, there was m less than omega where we stacked with the mn sharps, but sort of the next quantifier up from there is the ladder mouse. Okay, so a ladder, recall that m ladder is the least mouse such that there's a sequence, infinite sequence of ordinals. The theta n's are all m cardinals, and mn sharp of m up to theta n is a proper segment of this m, and it satisfies that theta n is wooden. We have partial woodenness. In the end, it follows that m will be, well, for the least one, so it follows that m will be closed under the mn sharps. This up to this point, it thinks that theta n is wooden, but then it will have more sets beyond there that kill where it's not wooden. So this theta n is only partially wooden in the model, and so in fact, the m ladder satisfies there are no wooden cardinals. It also doesn't model ZFC because if you take the minimal theta n sequence here with these properties, then it can define that sequence. So it's ordinals are cofomega definably over the model. Okay, so combining work of Rudamina from about 20 years ago and a few years ago from Wooden, OD12, the next level is equal to the reals of ladder mouse. Okay, so this is a variant of that. This result. So alpha here is projective-like gap, and gap, if you don't know, is an interval. Alpha beta is a gap of L of R. If it's a maximal interval with respect to sigma 1 elementarity, you just extend alpha and beta as far as you can in either direction, and any lower or higher, it would fail sigma 1 elementarity. That's a gap of L of R. So alpha alpha is a gap, means that you know, there's got to be sort of cofinally many sigma 1 truths that appear below alpha, and at the next level, there's also another sigma 1. Projective-like says that model J alpha of R does not model KP. Case we're in. Suppose alpha is a limit ordinal of countable cofinality, or it's a successor ordinal, and beta doesn't end a strong gap. This strong gap, the admissible gaps alpha beta get split into, I mean, non-projective-like alpha beta gets split into weak gaps and strong gaps. So this is a kind of beta here would be a certain kind of non-projective-like gap. Okay, so in these, then we get the OD alpha n is ODR alpha n is the mouse set here. So, and this is an analog. This works, well, I mean, not completely. This is partly analogous to what happens with the ladder mouse, but then there's, because, I mean, the fact that it works on a cone is, I mean, I think the fact that it works on a cone is known separately, but this gives, there's sort of an explicit proof that it works on a cone. It works analogously to the ladder mouse proof, but then to get it light phase, there's other stuff you have to do. Okay, so I'm going to sort of talk about stuff, things that go into this. Yeah, as I mentioned, Rudamina proves some other instances. Alpha, uncountable cofinality. Projective light, this is where countable cofinality. So this result I'm mentioning here, I haven't had time to try to work it out, but it might just follow from descriptive set theory arguments. I'm not sure, but I think I will talk about it in a model theoretic proof of this, and that proof should be. Okay, so we've got a gap just as before, so countable cofinality or successor, and not the successor of a strong gap, effective-like gap. Then there's a cone, so base real x0 for a cone, such that for every x there's a mouse over x and x0, so in the cone above x0. And there's a cofinal sigma 1 elementary map from some J alpha bar of reals M into J alpha R. I mean, the existence of this sigma was already well, known, but and there's sort of a unique sigma like this, such that we get the anti-correctness thing happening with respect to this map. So pi 2, I mean, with respect to truth over these two models. So the sigma is sort of the natural version of, this J alpha bar reals M is the natural version of J alpha reals and sigma sort of truth corresponding. It's sigma 1 and cofinal elementary, so this matches these two models up. So this is the natural point to consider for correctness. And it's, so the mouse is sigma 1 correct because they have this map, but it's not sigma 2 correct, but the truth inverts at sigma 2 to sigma 2 and pi 2 sort of thing. Okay, and then ladder mice at the end of a weak gap or a strong successor of a strong gap. So this is just going to be a vague statement of this, and there's more details in the paper, but there's not yet full details. There's just sort of one case that's explained in reasonable detail. And, yeah. Okay, so if alpha beta is a weak gap, or beta is the successor of a strong gap, then there's a clone of reals X such that there's a mouse, let's call it M beta ladder of that of X, final below over J beta at the end of the gap, which is analogous to the M ladder over J of reals. Okay, so the vague thing. It's not, although it's analogous in various ways, it's also quite different because it has wooden cardinals, in fact, has infinitely many woodens, especially has a particular wooden, its least wooden, and the ladder ascends to its least wooden. And so this is different to M ladder in the projective-like sort of case where the rungs of the ladder are cup points of the model, so there's no extenders overlapping those rungs. In this case, the rungs lead up to the least wooden, so they are not cup points. And difference, and there's other differences. The definition of it uses another mouse that's associated to the end of the gap that just precedes this ladder, sort of in one, in terms of quantifiers, which, yeah, just corresponds to the end of the gap, and the gap is a derived model of an iterative gap. The ladder's cofinal in the least wooden, yeah. No, I mean, it's definable over the... okay, so I'm going to talk a bit about the proof of the truth inversion stuff at the basic ladder mouse. And so this will be. So this, yeah, so this will... yeah, so we'll prove the anti-correctness result for the ladder mouse, so that it's sigma 2 over J of reals corresponds to pi, is pi 2 over J of the reals of the ladder mouse. I think. That's the main thing to look at. It also gives an alternate proof, alternate analysis of the ladder mouse that avoids the stationary tower that's used in Wooden's analysis earlier. So, but some of the setup is likewise, so we're just going to look at that. So first of all, pi 1 over J of reals is recursively equivalent to an infinite conjunction of projective statements. This is a recursive correspondence, so there's a recursive map on formulas, phi pi 1 formula mapping to a sequence of projective statements such that J of reals satisfies the pi 1 if and only if the conjunction of these projective statements is true. And then conversely, you can take an infinite sequence of projective statements and convert that to a pi 1 statement. First direction we were interested in. So if we take Tn as the standard tree that projects to a universal sigma 1 2n set of reals coming from the usual scale construction. And let's look at a pi 1 formula, which is phi, and the corresponding sigma 2 formula where we do exist the real W such that phi holds. So as I said before, sigma 2 and sigma 2r is recursively equivalent for over J of r, but convenient here to consider this version exists the real, so look at that. Okay, and so then we look at the natural tree that's attempting to, that will project to the set of reals X that satisfy rho X. So we're using these trees, the TNs, and we're building X and various witnesses. Okay, so T rho is the sigma 2 formula, builds X, which is going to satisfy rho X, and W and Y vector, which are some witnesses. W is the witness to this formula here. These are two reals. Y vector is just codes up sequences of ordinals which show you're in the projection of the TNs. Okay, so Y vector is a sequence of ordinals. It's an interlacing of an omega sequence of functions, each from omega to the ordinals, and we have that that tuple XWYN is a branch in Tn for all n. I guess with the formula. Yeah, the first entry here is the formula, and then there's W of the. Okay, so that, ignoring this last comment here, that already ensures that the projection of T rho is exactly the set of reals such that JR satisfies that. The last thing is that the first Y vector restricted n, so the first n ordinals in this sequence Y vector should only involve entries from the first n reals that we talk about here. These are the ones that correspond to the first n trees, and they're at a certain bounded level of projective complexity. So we just want to, at the first n levels, you should be sort of bounded into, you can see what bound you are in terms of projective complexity. Okay, now, if we've got again, phi is pi 1 and rho is the sigma 2 formula coming from quantifying there. If you've got any projectively correct model, then you can compute the version of that tree we just defined inside that projectively correct model, and it gives a nice version of the tree. Because it's projectively correct, it gets all of the relations on the pre-will order is correct, so it's a reasonable subtree of the true tree, and as it embeds in a natural way. So if you've got any larger any other projectively correct model n prime with a larger set of reals, then there's a natural embedding from the first tree into the second tree. In particular, you can embed it into the tree of V, the true T rho, in order preserving sort of fashion. And therefore, anything that's in the projection of the smaller tree is also in the projection of the larger tree. Okay. Okay, so now we want to consider this for n is m ladder. And if I've got any real in m ladder, we know that if the tree as computed, m ladder's version of the tree, so this is again some subtree of the true one, if that's ill-founded, then certainly that embeds into the true tree at x. If the section at x is ill-founded, then the true tree's section at x is ill-founded, therefore JR satisfies rho x. But I'm trying to think about now, can m ladder compute sigma 2 truth, right? So we've got its version of the tree, we can consider its projection and so forth. So if x is in here and this tree is ill-founded, then that certainly is true, okay? However, the converse isn't clear. There could be a real in here such that m ladder's section at x is well-founded, but the true tree is actually ill-founded at x, because it's the bigger tree. Okay, so you can't just use the tree directly. The Wooden showed dealt with this problem by showing that there's actually an ordinal less than the omega 2 of m ladder, such that for all those reals x, JR satisfies rho if and only if the true tree at x is ill-founded. Well, these are already equivalent. But this is equivalent to the tree, m ladder's version of the tree section at x is either ill-founded or has rank at least gamma. So it's fixed gamma, and ill-founded or rank above gamma means that the true tree is ill-founded, and so you know the sigma 2 thing is true. Rank less than gamma means that the true tree is well-founded, so you know the pi 2 thing is true. Okay, so you know the truth from this. And the proof of this uses stationary Tower forcing. Okay, and as a result, we get as a result, we get this theorem down the bottom. OD12 is the reals of M ladder. That comes from Rudolph's work that already showed one direction. All the reals of M ladder are OD12, the second direction. We can compute the sigma 2 truth over M ladder, and therefore we get all these definable reals inside M ladder. This gamma you can also get rid of definably over M ladder. So Steele showed that the parameter gamma can actually be defined over M ladder, and so you can remove it as a parameter. This doesn't, however, this doesn't seem to give the anti-correctness thing, which is give the optimal definition of sigma 2 truth over. So what about that? M ladder with pi 2 over JR is analogous to these other things where we had the truth inversion. So we want to try to see that, right? So we want recursive functions that take any pi2 formula phi, convert them into sigma2 formulas, and we should have that all reals of m ladder j of r, so in the one direction, j of reals satisfies phi x with pi2 phi, if and only if j of the m ladder's reals satisfies the sigma2 formula here, and conversely, the part 2 here is already clear from Rudimina's earlier work. So I won't talk about that. The one we want to look at is this. This is like the Spector-Gandy one for omega 1ck. So we have to express pi2 truth in a sigma 2 fashion over j of m ladder's reals. Okay, so it's going to be similar to the one for pi13 over m1. So let's remember how that goes. So if phi is pi13, then the reals satisfy phi of some x, where x is a real in m1, this should be. If and only if the reals of m1 satisfies this sigma 13 formula. The sigma 13 formula says there is a pi12 iterable phi x pre-witness. So phi x is the pi1 thing. Pi12 iterable is a pi12 definable condition, which is a sort of weak form of iterability. And phi x pre-witness is a first order condition on a pre-mouse. So it says it's a pre-mouse and it's a first order condition. So that's explained here what the condition is. And it basically says that we're going to force the pi13 thing over it with the extender algebra, forcing with the extender algebra. Okay, so we have the pi13 formula, which is of the form for all reals, some sigma 1,2 thing happens. And if we go to real, then a phi x pre-witness is just a pair, n and delta. N is a pre-mouse. X is a real that's in n. N satisfies delta's wooden and a bit more. And n thinks, the key thing is that n thinks is forced in the extender algebra at delta that tau holds of x, the real we care about, and the generic real, where z dot, where z dot's the generic real added by the extender algebra. Or you could talk about the collapse forcing if you want. Okay, so we're forcing a sigma 1,2 thing to happen about whatever this generic real is. Okay, and then you use genericity iterations to see that if you have such a thing and it's iterable, then you can iterate and make any potential counterexample generic and add it, and you prove that actually the sigma 1,2 thing holds about that. Okay, so Wooden heard that. Obviously, define the extender algebra and use that to prove this fact that if x is a real of m1 and these pi13, then these things are equivalent. The real satisfies the pi13 thing. There's an iterable phi x pre-witness, or there's a pi12 iterable phi x pre-witness, which is in the reals of m1. So there's an extra fact here that every real that's in every pre-mouse that's in m1, which is pi12 iterable, is fully iterable. So although pi12 is a weak form of iterability. So this gives a sigma 1,3 expression about that pi13 statement. Okay, so what we want is to do this for the m ladder level. So for pi2 formulas should convert to sigma 2 over here. So basically we should expect that this formula should say there is a pi1 iterable phi x pre-witness. So pi1 iterability was already defined by Rudimina, and it's pi1 over jr, definable. It basically says that you're iterable with respect to iteration trees that are projectively guided at some projective level. If you get up to a point where you've got a ladder mouse, then you've gone through things where you've sort of gone through all projective levels, then you can't really say anything beyond that point. And so you lose track of things there. Okay, so it's good for things that are below m ladder. M ladder is sigma, so pi1 iterability is expressible in this way. M ladder is sigma 1, so pi1 correct. So it's correct about what pi1 iterability is. And every pi1 iterable pre-mouse in the reals m ladder is fully iterable, like the pi12 for m1. And so if we say this interpret this in m ladder, then the pi1 iterability guarantees full iterability. So the key question is then we just need to formulate what a phi x pre-witness is for this. Okay, and so it should be something like the pi13 version. However, you can't do it directly because we don't have full woodenness with respect to sort of all the mn sharps simultaneously. So what you would, direct analog would be you've got a wooden and it's wooden with respect to all projective, with all mn sharps, and then you can say it's forced in the extender algebra that there is some witness for this thing, that the pi1 thing happens. sigma 2, so no, it's pi 2, sorry, yeah. So it's forced about every real that there is a witness to the statement that's at some mn sharp level. Okay, so we can't do that because we don't have woodenness at that sort of level. So, okay, and so if you try to argue directly by, I don't know, looking at iterating the full M ladder and looking at what it thinks about iterates, it's hard to understand the elementarity you would sort of need or something to pull back. When you have sort of weak elementarity and things like this. So, okay, so I want to, how much time have I got? Okay. Yeah. Okay. So I'll try to sketch how we can deal with this. Okay, so we want to look at partial ladders. So these are just like sort of like the M ladder cut off at some one of its levels, basically. So N partial ladder is where you have a finite tuple theta vector, N plus 1 tuple. These are just sort of like the first N plus 1 rungs of the ladder. The theta I should be an N cardinal. Capital N's a pre-mouse. Theta I is an N cardinal for each I. Theta N, the top one, double successor in N is the largest cardinal of N. N's closed under all the MK sharps for every K. So N will be projectively correct. And this Mi sharp of N up to the theta I is the Q structure for theta I. So that's the level where it is. It's the largest level where theta I is wooden in that segment. We take theta I, the least such theta. I just want the, doesn't really matter so much that's least such theta, but for notation, theta vector N is this, then, that uniques the tuple theta vector, and so that's determined from N. Okay, that's an N partial ladder. Yeah, and then just a bit more notation to do with the tree. We want to consider versions of the tree where we collapse where we collapse one of those theta i's over one of these N partial ladders, and then we've got the tree in there. It's still projectively correct, so you have that. Okay, so the notation for that is just this here. So N is a pre-mouse, theta is some cardinal of N, the double plus exists. N is projectively correct, it's MK sharp closed up. And then S theta N is just the version of that, sorry, rho is fixed, is a sigma 2 formula, and I'm just ignoring that in the notation for S here. So, but S theta N just means you collapse theta to be countable over N, and then look at the version of T in that NG. Okay, so the tree that's computed inside NG. If I've got a further N primed, and N is N is not an initial segment, but N up to its theta plus is an initial segment of N primed, and they agree that is, theta plus is the successor in both of them. So this would be sort of like capital N is an N partial ladder, and N prime is going to be an N plus 1 partial ladder or something, but they agree in terms of this level where the first N, that rung of, the top rung of N is going to correspond to one of the rungs of N prime. Okay, so if we have this, then we can embed the version of the tree in the collapse of theta over N. This is this Sn theta into the collapse, into N prime's version in its larger collapse of theta primed. In the way as described before. Right? So these are projectively correct things. They have the versions of the tree. You can embed them like this. Okay, and a key fact here, Hjorth's lemma is that these things are all independent of the generic you choose, and so they're in N primed, and well, Sn theta is in N, and these things here are in N primed. So generic you choose doesn't affect the tree you get and the way it embeds into it. You get it all in the model. Okay, so here's the motivation for sort of how we define the phi x pre-witness. What we want is a phi x pre-witness or witness. Witness will mean it's iterable. Pre-witness is the first order part. So what we want roughly is an iterable zero partial ladder that has x in it. So we're looking at phi x. Phi x is pi 2, rho x is the sigma 2 formula. We want an iterable zero partial ladder that has x in there, and player 2 should win in the following game we're going to define. Okay, and the game goes like this. The player 1 starts by playing an iteration tree T0 on P0 based on the first rung of the ladder. So take the and it should have successor length. Take the last model, and the theta prime 0 is the image of theta 0 now. Player 1 also chooses some S0, T0 in the version of the tree you get by collapsing that theta prime 0. Length should be 1 for that node. Okay, and then player 2 plays a 1 partial ladder, which is a segment of this iterate P prime 0, proper segment. And it agrees up to this point that the cardinal successor of that first rung, right? So it has one more rung because it's a 1 partial ladder. And the key thing is there's a proper segment here, so there's a drop in models happening. Player 1 then does the same kind of thing again, but now it's on P1, and the next iteration tree is above theta prime 0, so like this. Take the last models and stuff, and then S1, T1, and then, yeah, so S1, T1 is going to be in the tree over the iterative P1 primed after you collapse the theta 1 prime, so collapse more. And the thing is that S1, T1 should basically extend what S0, T0 was doing, but after you embed it up into the next tree. So as you're going along, player 1 is trying to produce prove the sigma 2 thing is true by putting together a branch through the full tree in V. Player 1 is trying to prove the pi 2. So does that. Player 2 again then chooses a 2 partial ladder, which is a proper segment of P1 primed and extending the right level and so on. Okay, so you iterate up and you have to drop down to, at every step you have to drop down to a proper segment and so on. And then player 2 wins if it goes forever, otherwise you have to follow the rules. Okay, so if it's iterable and player 2 wins, then JR satisfies the pi 2 formula, because otherwise you iterate to make the reals generic and the witnesses generic that things get into the, so if the sigma 2 thing is true, then there's this W and Y vector that witnesses that gets into the true, is a branch of the true tree, and you just do the iterations, the T0 and T1 and so forth are iterating to make sort of these things generic to make sure that you get things in the trees, make sure you get S0, T0 that you can plug in and so on, S1, T1, corresponding to this. You can keep going with that, but because it's iterable, it can't go forever because you're dropping in model, and so it's impossible. Okay, so if you've got an iterable one, this is true here. The pi 2 thing is true. And okay, then we want to convert, so then you just want to sort of use that idea, that's what you want to get out of a pre-witness. So now you formulate pre-witness to be in a first order fashion that you can get and then prove that those things exist, right? So the pseudo definition here is just basically internalizing what we want from that strategy. You can do the same game, but make sure you have to sort of require that the strategies you're using actually in the premise to begin with, and except that you don't play any iteration trees here. So all the trees are trivial. So all that's going on now is player 1 chooses an S0, T0, and then player 2 chooses a proper segment to drop to, and then S1, T1, proper segment to drop to, and so on. But you've got to also play the iteration, the strategies for the game as you go along, then you've got to keep following them. So anyway, in the paper, there's a formal way of saying that here. Okay, and then you have to prove that those things exist. So, so that's this lemma. If I have a real in S infinity is just the direct limit of the S theta ends. Working in M ladder, we can collapse any of the rungs of M ladder and look at the tree there. Yeah, okay. They all, one embeds into the next one because you're enlarging the reals as you collapse more and more. So that's this direct limit of trees over M ladder. That's the S infinity M ladder, okay? So this tree is definable over M ladder. It's sort of, literally, it's not a subset of M ladder, but in the codes, it's definable over M ladder. Because, these maps that we were using were in there and they're easily definable and stuff. Okay. So the key lemma is this, that if I have a real in M ladder, then these things are equivalent, that JR satisfies phi, the pi 2, this is pi 2 formula here. We know that this is equivalent to not being in the projection and so forth. Okay, but that's equivalent to X is not in the projection of M ladder's S infinity here. Okay, so there's just this small version of the tree that's good enough to compute the truth for these reals. And that's equivalent to there being a phi X pre-witness, which is a segment of M ladder up to its. That thing then is expressed in the right sort of fashion, the sigma 2 over JR. the proof of the key thing to do here is to go from the red one to the blue one. So if this is well-founded, then there's a phi x pre-witness, which is a proper segment. Since the proper segment is iterable, and that'll guarantee that the pi2 thing by the previous lemma. So we want to go from this being well-founded to this. Well, the fact that this tree is well-founded means that we can rank it, and you just prove by induction on the rank of the nodes in the tree that there are pre-witnesses sort of at those corresponding nodes all the way through the model. And so you're sort of putting together all these structures that you see all the way through the model. But at n nodes of the tree, they're just sort of trivial. They're just like things that sit, they're just sort of segments of the model. And when you go through by the inductive step, you sort of only go up one level at a time, and it's first order to put together the things you need, and you can take holes into this. Okay, that's
the rank's probably bigger
than. Yeah, but. Okay, so that's a vague idea of how you do it. But I should move on. Okay, just a brief mention about the light-face Mouset theorem here. I mean, there's a version on a cone which sort of comes directly from so you can adapt this stuff to J alpha R. The stuff I've done so far, you can adapt to J alpha R on a cone for the right countable co for alphas here. But to get the light version, you need to do something else, light phase version. So here, basically you want to look, so this is similar to what happens in the light phase version of the Mouset theorem for limit levels of bar. It's a Wooden's result there. But we want to do a local, you sort of need to do, I think, you want to do a local KC construction and sort of as much locality as possible. So the difficulty is that the rungs of the ladder in the M ladders are not fully wooden. So if you do a full background LE construction, then sort of continue on after there, it seems it might project across that, and that sort of messes up the construction. Okay, instead if you do a local KC construction, then you never project across a limit cardinal, and so these things are stable and things like that. Q local just means that it's P construction at every local wooden cardinal, so you automatically absorb the two structures match up. And then this model here, the output of this is the Mouset theorem. Last slide is this one, the end of the week gap, and yeah, I'm probably out of time though, so okay.